Good day, everyone. My name is Shihao Wen, and the first topic I'll be presenting today is a fire detection solution using fiber optics, specifically for complex environments like theaters. This is based on a FOSA webinar showcasing NKT Photonics implementation of linear heat detection using distributed fiber optic sensing, commonly known as DFOS. Here's the outline of my presentation. I'll begin by introducing DFOS and the basic idea behind linear heat detection. Then, I'll explain how this technology applies to fire protection, especially in large enclosed areas. I'll walk through why high resolution sensing is so critical, how the system is installed, and finally, how everything comes together to ensure safety. DFOS is a type of sensing system where the optical fiber itself becomes the sensor. Unlike traditional point sensors that detect only in fixed locations, DFOS uses backscattered light to detect changes along the entire length of a fiber. This makes it ideal for continuous monitoring over long distances. In LHD applications, when a fire or excessive heat source causes a temperature increase at any point on the fiber, that change can be precisely located. It's fast, reliable, and scalable. Theaters are an excellent example of where traditional smoke detectors often fall short. Think about all the curtains, lighting rigs, backstage areas, and acoustic panels. Fire risks are high, but visibility is low. With DFOS installed discreetly above the ceiling or along the stage rigging, we can create a heat map in real time. This allows theater operators to respond quickly and accurately to any unusual temperature changes before a fire spreads or is even visible. The real strength of this system lies not only in detection, but in prevention and response. We're talking about pinpoint accuracy down to the meter. With instant alerts, it integrates well with automated safety protocols, like turning on sprinklers only in affected zones or guiding audience evacuation via digital signage. The thought process is detect early, react intelligently, and minimize damage and risk to human life. Now let's move into the second topic, mid-infrared spectroscopy for water and wastewater analysis. This presentation is based on a paper published through SPIE by Max IR Labs. The system combines IR absorption techniques with fiber optics for real-time in-line monitoring of water quality. We'll start with a basic introduction of the technology, then compare the types of IR detectors used. I'll explain how special fiber coatings enhance performance, how the detection limit is lowered, and how background interference is minimized. Lastly, I'll summarize the key takeaways and practical value. One major challenge in water analysis is that water itself absorbs mid-infrared light very strongly. This makes traditional IR measurements very difficult. To overcome this, Max IR Labs developed a system using silver halide fibers, which are flexible and transmissive in the mid-IR range. They added an ion selective coating on the fiber surface. This coating traps target chemicals like nitrates or PFAS, pulling them close to the evanescent field of the guided IR light, thus amplifying their absorption signal without needing bulky sample containers or high-powered lasers. The team compared two types of IR detectors, one cooled with liquid nitrogen, Allen 2, and another using thermoelectric cooling, TEC. While Allen 2 cool detectors are extremely sensitive, they are large and they are inconvenient for field use. TEC detectors, on the other hand, are compact and more practical. Rather than relying only on manufacturer specs like detectivity, the researchers monitor signal noise and absorbance stability over time in real conditions. This approach gave a much more realistic view of detector performance. Let's take a closer look at the coating. By immobilizing molecules near the fiber's surface, it effectively turns the fiber into a chemical filter. Only the target substance get trapped and measured. This improves signal to noise ratio dramatically, and because the sensing range is very short, only about 3 microns from the fiber surface, it avoids interference with water itself. This enables detection even at room temperature, which is a major step forward in portable water testing. To sum it up, this fiber based IR system enables rapid, selective, and real time water quality analysis. It's highly adaptable, scalable, and can be deployed in, in environmental monitoring, industrial process unit, or public water safety. The combination of advanced fiber materials and smart coatings truly unlocks new potential in chemical sensing. Now, on to the third topic, biomimicry in photonics and fiber optic sensors, and particularly in soft robotics. This approach draws inspiration from nature to solve engineering challenges in sensing, motion, and communication. By looking to the biological world, engineers are finding creative and efficient ways to enhance photonic systems, especially where flexibility and adaptability are the key. I'll highlight 3 case studies: secure signal hiding based on hatchetfish camouflage, object handling from twinning plants, and wall climbing motion from inchworms. Each one shows how a biological mechanism inspired a functional solution in either microwave photonics or fiber optic sensing. We'll explore how these concepts translate into practical engineering tools. Nature has had millions of years to evolve solutions to complex problems, whether it's sensing danger, moving efficiently, or staying hidden. Engineers are now borrowing these solutions by combining biology and photonics. We can build smarter systems that are safer, more adaptable, and capable of operating in environments where rigid machines fail. This approach is especially powerful in soft robotics and in environments that demand both precision and resilience. Let's begin with hatchetfish. It lives in deep ocean waters and uses specialized reflective scales to essentially vanish by reflecting ambient light in a way that hides its silhouette. In photonics, this inspired a technique called steganography, hiding information in plain sight, such as embedding a message within a carrier wave. In radio over fiber systems, we can hide secure data by manipulating light phase or polarization. Unless you know the exact modulation key, the signal is undetectable. It's nature's stealth, reimagined for secure communication. Now we have twinning plants. These plants climb by wrapping themselves around nearby structures. Inspired by that, researchers developed a soft robotic gripper that spirals around objects using pneumatic actuation. Inside the soft body, fiber optic sensors are embedded to measure pressure, curvature, and contact points. This allows the robot to estimate the shape and fragility of an object, making it ideal for precision tasks like handling medical tools or delicate agricultural produce. Lastly, Consider the inchworm. It climbs using alternating grip points, anchoring with one end while pulling the rest of its body forward. A climbing robot inspired by this mechanism was developed using suction pads and a flexible body. Fiber Bragg grading sensors embedded in the body track real time strain and position, allowing it to adjust to curved or uneven walls. This kind of robot is useful for industrial inspection or surveillance in areas inaccessible to traditional machines. Biomimicry in fiber optic and microwave photonic systems allows us to build tools that think and move more like living organisms. From secure data transmission to adaptable gripping and climbing, these innovations merge biology with advanced engineering. As we keep learning from nature, we'll continue unlocking smarter, more resilient technologies. Finally, let's talk about smart infrastructures, specifically fiber optic sensing for highway monitoring. This content comes from OptaSense and explores how distributed sensing can make roads safer and more intelligent. Distributed fiber sensing, DFS, turns standard optical fibers into continuous sensing elements. By analyzing changes in light backscatter, it can detect vibration, strain, and temperature along the fiber in real time. There are three primary backscatter effects: Rayleigh, Brillouin, and Raman. Rayleigh is sensitive to dynamic strain and is ideal for vehicle detections. Brillouin can measure static strain, like ground subsidence. Raman is used mainly for temperature. Each type adds a layer of information to road condition monitoring. Advancements in optical signal processing and fiber interrogation units now allow us to monitor tens of kilometers with sub-meter resolution. More importantly, the cost and power consumption of these systems have decreased, making deployment more scalable. Highways and bridges naturally deform over time. With fiber sensors embedded in the concrete or roadbed, we can detect early signs of stress, corrosion, or cracking. This kind of predictive maintenance can prevent catastrophic failure. The system also tracks road surface integrity. Fiber optics detects anomalies in vibration patterns that could signal potholes, rutting, or layer separation. Besides infrastructures, it also measures traffic. Vehicle-induced vibrations can be analyzed to calculate speed, density, or even classify vehicle types. With curve fitting and signal correlation, we can generate real-time traffic maps for better traffic flow management. In summary, fiber optic sensing gives us a passive, cost-effective way to turn highways into smart assets. It provides the data needed to maintain safety, reduce congestion, and build the future of transportation. Thank you for listening. That concludes my final presentation.